Video, we're going to cover Chapter 9, specifically Section 9b and 9c, which is just working more with modeling with lines and modeling exponentially. 9b is all about modeling with lines. 9c is all about modeling with exponents. Just gives you more word problems to look at, see how the numbers can change the layout and your future values. The one thing I will mention is on the exam, you're not necessarily going to know that this question is from 9b or this question is going to be from 9c. So the most difficult thing between going from the homework and going to the exam is that in the homework, because you're working in a specific section, you already know, oh, all these problems are going to be lines. All of these problems are going to be exponential, depending on what section you're working in. In the exam, it won't necessarily be that way. So one of the things we want to work on today, make sure that we're practicing as we read these problems, is what in the question is telling us this is a line problem, or what in the question is telling us this is an exponential growth problem. So I have a few examples over here on the side from 9b and 9c. I didn't even put what section it comes from, just to remind you guys that you're not necessarily going to know. But we'll go through some of these examples and get ready for our exam next week or late this week. Okay, so just recall, we have two equations that we are most familiar with from last week. Y equals mx plus b. This is the linear model. And q is equal to q naught times 1 plus r raised to power t. Oops, the exponential model. The thing we want to keep in mind is when do we use each model? So just as a reminder, the linear model is going to happen when we have a constant rate of growth or a constant rate of change. It doesn't necessarily have to be growth. It could be decreasing. But if it's decreasing by that same amount over and over again, then we're looking at the linear model. For the exponential model, we're looking at a constant relative rate of change. So rate of change expressed as a percent is a good way to think of it. Chapter 2, which seems like an eternity ago, we talked about the difference between absolute change and relative change. Absolute change is happening in a linear model. For example, we have a growth of 120 cases per day, right? That same number, 120, 120, 120, keeps adding to the amount over and over again. Then we're modeling a line. Whereas if the rate of change is being expressed as a percent, then we're talking exponential model. So the rate of cases is growing by 12% per day, right? That means something completely different, that the growth in day 1 is going to be much different than the growth on day 10, and we're looking more at an exponential model when they give it to us in terms of percent. So just keep that in mind. Also remember the roles of these letters, that our m is our slope. We've talked a great deal about slope. Our b value is the y-intercept. Same over here, we have this initial value, which plays the same role as b in the line. Q naught is that initial amount. And then the r value is our rate of change. That could be a positive or a negative number, and it needs to be expressed as a decimal. So we're going to look at two examples. First one I want to look at is this problem here. It's example 7 for us. We'll go through the whole process of modeling, really. One thing I will mention before we do this problem. These models that we're talking about right here are only as good as the range of data that we have to work with. So, for example, if I have a linear model that's talking about the growth between, I don't know, I'm just going to make up a nice example. Let's say I'm interested in the growth of oil production between 1990 and 2010, for example. And I have maybe it's a line or something that's telling us the way that oil production grew during this time. This model is really, really good for telling us about data that happens in between 1990 and 2010. So this would be a great model if I wanted to estimate what was happening around, I don't know, the year 2000 or something. What this model is not good for is what's called extrapolation. Extrapolation means I'm going to take this model and I'm going to try to use it to figure out what's going on way beyond the range that's given to me. And that's not good math. The reason why is because we don't know what's happening in this range over here that could possibly affect this line graph. Maybe it's not a line anymore. Maybe it's flattening out, or maybe Donald Trump got elected and decided he was going to pump a ton of oil between 2016 and 2020, and there's this huge sharp increase in here. Because we don't have any data between 2010 and 2015, this model is not a good indicator to predict what's happening way in the future. Okay, so we like to look at values that are in between our lower and upper bound in terms of prediction. Okay, another thing to keep in mind, we mentioned this in the last lecture as well, time is always going to run along our x-axis for these problems. Does it always run on the x-axis? I can think of maybe a handful of examples of the many, many, many thousands that I've seen in my life where time isn't on the x-axis, but they're very, very rare, and it's not something you're going to see in this book, on our exams, or any of that. So if you're ever worried about, okay, I have two unknowns here, which one is my x, which one is my y, as a rule of thumb, you could probably just say right off the bat, your time is going to be your x value. Okay, it's going to be your independent variable, the one you plug in for. All right, so let's take a look at these two problems. Okay, so example 7 that I have over here on the side says, suppose your dog weighed 2.5 pounds at birth and weighed 14.3 pounds 1 year later. Based on these two data points, find a linear function that defines or describes how weight varies with age. So in this problem, they told us specifically, I want to use linear in here. And so right away, I'm going to start out by giving slope-intercept form, y equals mx plus b. And it told us to write a function how weight varies with age. So our x value is going to be age, and our y values in here is going to be weight for the dog. So we have two data points. They told us that the dog weighs 2.5 pounds at birth. So at age 0, we'll say, the dog's weight was 2.5 pounds. And then 1 year later, at age 1, we'll say we're measuring age in years in this case, the dog weighed 14.3 pounds. So our weight is being measured in pounds. Our age is being measured in years. First thing it says is we want to make an equation used to model this situation. Remember, we're using y equals mx plus b, so there's two values we need to find before we can build our model. We need to find the slope, and then we need to find the y-intercept. The y-intercept is actually given to us in this particular problem. The y-intercept is a value that happens when the x value is equal to 0. Remember, we talked about this on these problems as kind of like a starting point, just like Q naught is in the exponentials. So this starting value right here is actually our y-intercept. It was given to us in this problem, and I can say right away that the b value is going to be 2.5. Now I got some work to do in order to find slope. Remember that slope, our m value, is the rise over the run, or in other words, the change in y over change in x. Over change in x. So in this problem, we're going to subtract the y values on the top. I'm going to take 14.3 minus 2.5. And on the bottom, I'm going to subtract the x values in the same order. So the bottom one minus the top one. 1 minus 0. When I simplify this, I get 11.8 over 1. And remember what the units are of these. It's extremely important. I could definitely ask you as you calculate this, what unit is the slope in? Remember that these values up here are pounds, and these values down here are years. So when I divide this, 11.8 divided by 1 is saying that this dog's weight is going to grow 11.8 pounds for every 1 year. Or in other words, the M value is 11.8 pounds per year. Now we have the B value and we have the M value, and so we can write out our equation. Be careful with Web Campus, or I'm sorry, with MyMathLab. They like to use different letters instead of Y and X sometimes when you're modeling, just to be difficult, frankly, and to make it more specific to the problem. In this case, they wanted you to use W as the Y value because W is representing the weight, and T is going to represent our X value. They'd rather use T for time than X. So you could start out by writing it as Y equals 11.8x plus 2.5. But for MyMathLab, we want to change that W and that X, or that Y and the X to W and T respectively. So the equation that they're looking for is W is equal to 11.8 T plus 2.5. This is our equation that models the growth of the dog for every year that it's alive. Now let's stop for a second before we go any farther and just talk about the practicality of this problem. So when I look at a dog's weight between when they're born and when they're a year old, is that a good indicator of how they're going to grow every year after that? So, in other words, does a dog grow as fast in the first year as they do every other year after that they're alive? Well, no, of course not. Dogs grow a great deal that first year, and by the second year, they're pretty much full grown. So, is this going to be a good indicator of how big this dog is going to get over time? Probably not, actually. We'd want to take a linear average over many, many years. Probably not when the dog's a puppy and as it's growing, because assuming that it continues to grow that way, you're going to have a giant dog pretty soon. So, it asks us to use this model to find out what the weight of the dog will be after 5 years and what the weight of the dog will be after 9 years. And they want us to round to the nearest tenth. So the value of 5 years and the value of 9 years, those are going to be values for T. So in other words, I want to take this model and I want to plug in T equals 5 into it. And it's going to give me what we expect the weight of the dog to be in 5 years. So I'm going to get W is equal to 11.8 times 5 plus 2.5. Whip out our trusty calculator. We go 11.8 times 5 plus 2.5, and we get 61.5 pounds this dog weighs. W equals 61.5. Remember, we want to put the unit on these problems. Weight is being measured in pounds. Similarly, you could do the same thing for part C in this problem by plugging in T equals 9 into this equation and finding out how much we expect the dog to weigh after 9 years. Now, like I said, this probably isn't a very good model. The next statement asks us to describe the validity. I would say this model is, let's see, it says, let's look at these. I would say that this model is not accurate. So anything that's telling me about it being accurate, I'm pretty much not going to listen to. So definitely not A. The B says the model is only accurate for large ages because when a dog is young, it grows faster than when it's older. I like that answer right there. The problem with this is that we used a range from 0 to 1. And of course, we mentioned dogs grow really fast when they're first born. If we would have used a linear model, I don't know, maybe between the age of 4 and the age of 10, then we could have most certainly predicted the dog's weight at 5 years and at 9 years. But we're outside of that range. We're only looking from 0 to 1. So using that model to predict at 5 or to predict at 9 is not a very good thing. And so we get that the dog's weight, according to this, is 61.5 pounds. But I can tell you right now, it's probably not a very good model. The dog started out at 2.5 pounds and weighed 14.3 pounds later. I would be shocked if this dog ever got bigger than maybe 25 pounds in its life. And according to this, it's already at 60. And if you were to plug in 9, you're going to get something ridiculous like this dog's over 100 pounds. And the dog that started out weighing 2.5 pounds at birth, I doubt was ever going to reach 100 pounds. So this is a good linear model example. Remember, it has two components to it. It has finding the slope, which we've done here. In this particular problem, because we knew what was happening at time 0, we already had the y-intercept. You can also look at the video from graphing lines and linear equations to get more information about finding this intercept if we don't have a value at 0. So let's look at one more example. Look at example 1 from this section, and it says, consider the following case of exponential decay. So this problem as well straight up told you, hey, this is exponential. But remember, in chapter 8, in the very beginning of chapter 8, they weren't so nice. They would just give you a situation and ask you, is this linear or is this exponential? And you can expect the very same thing on the exam. So going through these problems, there should be specific words in there that speak out to you as far as what kind of modeling you're doing, even if they don't give you this value up here. So we look at this example. It says a privately owned forest that had 1 million acres of old growth is being clear cut at a rate of 7% per year. Here's your big indicator that you're going with exponential, even if they didn't tell you in the problem. 7% per year, we talked about that being a relative rate of growth, or a percent change in our rate of growth, immediately tells us that we're looking at exponential. So we'll start out, we'll say exponential growth or exponential decay. The exponential model we know is Q equals Q naught times 1 plus R raised to power T. Oops. And what told us we were looking at exponential in this problem? It said cut at 7% per year. So we want to make our R value here 7%, but it's a negative 7% because we're losing value. So this one is losing value over time. So our R value isn't going to just be 7%, it's going to be negative 7%. And we always want to express that as a decimal, in this case, negative 0.07. So this is our R value. Remember that Q naught is your initial value, or how much you started out with before you started applying the exponential decay. It told us that you originally had 1 million acres of forest. It's also important to know what unit Q naught is being measured in, because Q, this value over here on the left, is going to be being measured in the same value. Okay, so this whole model is telling us how many acres are going to be left over a period of time. And time in this case, they told us, is being measured in years, because this rate here is 7% per year. So that gives us our model in terms of time as well. So the input is going to be years, and the output is going to be acres. So let's start by writing this model out. It's going to be Q is equal to, our Q naught we said was 1 million, times 1 plus a negative, which I'm just going to write as minus 0.07, or 0.07 is fine too, raised to power T. Always combine like terms in here. You don't have to leave it as 1 minus 0.07. If something is losing 7% per year, then it's retaining 93% every year. And so that's why our inside piece becomes 0.93. Don't forget your million on the outside. Use commas if it helps. And here's our model. Q is equal to 1 million times 0.93 raised to power T. We can use this table now to show how the growth is changing over time. So we can fill in a chart. We start out with 1 million. I multiply that by 0.93, and then I want to raise it to, whatever power I'm looking at here over there in years. I want to fill out all this chart actually from 1 to 10. So you'll have to do these calculations on their own. It tells you to round to the nearest whole number, so be aware of all that. Looks like in the first one, I got 930,000. So I'm just going to make like a T and Q thing over here. And at time 0, I had 1 million. At time 1, I have 930,000, just a 0. And I can continue running through this 1 million times 0.93 raised to the 2nd power. We can see after 2 years, now I'm down to 864,900 acres. I'll do one more. I'm going to, how do I can recall. Oh, no, it didn't work. I'll type it in. 1 million times 0.93 raised to the 3rd power. We can see that we're continuing to lose acreage. After 3 years, we're down to 804,357. And again, you can continue typing through those as we go all the way down to 10 years. And then the last thing it tells us is to make a graph. You could sketch a quick graph of this. It's probably not a bad idea. And over time, as you see these, you'll begin to just look at the pictures and know exactly what it looks like. Remember that it's losing value over time, so any of those options over here on the right that are growing as you read from left to right, so like D, for example, is increasing as you read from left to right, so you definitely don't want that one. That's an increase. Also, things that are decreasing in terms of a line is no good. And also remember that at time 0 that you should be at 1 million acres. So way up here we should have 1 million. I'll say maybe this is 500,000 right here, somewhere halfway. And if you wanted to, you could make each one of these lines like 100,000, 600, 700, 800, 900, 1 million. So each of those is going to be 100,000. At 0 means that you haven't gone up or down any at this point. And so at time 0 over here, we should have a y value of 1 million. So our first point along the y-intercept is going to be all the way at the top here. And then we can kind of just plug in. At time 1, 2, 1, 2, 3 here. At time 1, it's at 930,000, so just a little bit below 1 million. At time 2, we're at 864,000. So just between the 900 and the 800, and then at 300, at 3 years, we're at 800,000. So maybe we're around here, and we can see that we're slowly coming down. I didn't do a very good job here. It looks too linear. Shouldn't be an exact straight line. Sorry. 2, and my 1 is like right here. So we have like this curve thing that's happening. Slowly but surely we're curving downward as we come into a landing. So which of these is it? I would say it's this one here. You can see that this one is dipping down way too much. Another good way of checking is to see what's happening after 10 years. If you weren't sure between those two choices, you could say, oh, well, what's happening at the very end at 10 years? Plugging 10 into this equation, plugging 10 in gave me about 483,000, roughly. And so, or 484,000, really, roughly 484,000. So at the very end, way over here at 10 on your line, you still should be above, or just below 500,000, right? 480,000, probably going to be right here. And so you should be looking for one that still has about half of its gap in it at the very, very end. And so that really makes me think in this case that it's B. A has too sharp of a decline here. We can see that in the A picture, we really don't have enough height. And so that's pretty much it in terms of graphing, and also in terms of input and output and things that we need to look for exponential and linear modeling. On the exam, Chapter 8 and Chapter 9 are going to be kind of fused together. Those problems will pretty much just include the main concepts from both of those sections. Things that you should be familiar with: slope-intercept form, calculating the slope, calculating the y-intercept, identifying the difference between linear and exponential growth, modeling in the exponential sense, plugging in points.